All right, we're almost there. This is the last, so this would be the new type of material of stuff we've done since exam three. Um, three types of questions to be able to address, and then a couple from the mastery that would be good to know how to do. Okay, so let's start here. This is question 2 from that part of the review. Find the exact value of this definite integral. So what we have to do is we have to get the antiderivative, and then we plug in the limits here, okay, from 3 to 5. So it's a definite integral. Remember, this is 1 over x squared. This 10 is a constant. You could kind of bring it out in the front. Just don't let that bother you. So just think of this as 1 over 1 plus x squared. And what you have to remember is this matches up with the, this integrates into the inverse tangent. Because if you take the derivative of the inverse tangent, this is what we ended up getting. And then we've got this 10 on the outside, so we multiply by that. So that just kind of do it. But this part here, we just have to recognize that when we integrate this, we get inverse tangent. And then we put in our lower limit and the upper limit and subtract the two. So it's, I don't know why I do that. I was seeing it, I saw 15, and then I think 16, I don't know. Okay. And probably during this week it becomes worse. So the exact value is going to be 10 inverse tangent of the square root of 15 minus 10. Now you could all put that out at the other, right? We could factor out the 10 if we needed to. The inverse tangent of 3. Well, that's an exact answer. Thing is, let's see what happens. Because I think if you take the inverse tangent of either one of those, let's see, I am in radian mode, which is what I want to be. Let's see, square root of 15. I wouldn't expect that that's going to be anything other than some kind of extent, so I can't write that. That's not going to, you can't exact that. And I think the same thing is going to be true when we take the inverse tangent of even 3, right? We get some sort of non-repeating decimal. So since they want the exact value, we're just going to leave it like this. Now, if they wanted it as a decimal, we would, take each of these times 10, do the subtraction, and we'd get a value. Okay, but exact value, this is good. And if it's multiple choice, they could have wrote this as 10 and then inverse tan square root of 15. The answer might look like this, right? So just be prepared to find either of the answers to match them up to see these algebraically what are the same. If it's open answer, either one is acceptable. However you want to do that. Okay, evaluate this indefinite integral. So this is where if we don't have boundaries, when we basically find the antiderivative, we are going to use a plus c. Okay, so, but with this kind, it's go, okay, what is this like a quotient rule thing? Well, no, let's do algebra first, simplify. So we're going to divide each of these items by x squared. So 5x to the 4th divided by x squared is going to be 5x squared, right? 4 minus 2. Negative 8x squared, that's just going to be negative 8. X squared divided by x squared is 1. Over here, we're going to get 3x. It's going to be 3 over x. I'm going to write that as 3x to the minus 1 And then we get minus 2 divided by x squared, so that's going to be minus 2x to the minus 2. Now there's going to be one particular problem child, and it's going to be this one, because we're going to have to do this differently. So let's just kind of go ahead. So we're going to integrate, find the antiderivative. So we add 1 to the exponent, right? The way we do this, add 1 to the exponent, and then divide by that new exponent. So that's going to give us 5 over 3 x to the third. Okay. Get to negative 8. That's just going to become negative 8x. Think of this as x to the 0 power, add 1 to it, so that's x to the 1 power divided by 1. Now this is the problem. This is one where you're going to say, okay, let's add 1 to this exponent. But if we do, negative 1 plus 1 gives us x to the 0, which means we just have 3. What we have to remember is, thinking this is a derivative of something. How do we get a derivative of negative x to the negative 1, or 1 over x? What it had to come from is natural log of x. If we take this derivative, we get 1 over x. And then this 3 is just viewed as a constant. So when you do that one, you have to remember, okay, this one is sort of a strange one. It's 3 natural log of x. So when you take this derivative, you get 1 over x, or x to the minus 1. Okay. Now it's different for x to the minus 2. We can add 1 to the exponent here. Nothing too strange happens. We get x to the minus 1. And we divide by that new exponent, which is going to be minus 1, right? So I'll just write it minus 2 plus 1. So it will be minus 1, so that becomes a positive. So what we're going to get is we're going to get plus 2 x to the minus 1. And that can go down below. And then just remember here, there's also the possibility we had a constant. So the thing is if we take, so this is the antiderivative, sort of the original function, that if we were to take its derivative, we would get back to what we started with. Okay, maybe not, we wouldn't get back to this, we'd get back to our algebraically simplified function. And so you could kind of do that, right? So this is our check. So we are done right now. This is our answer. Should find it either in the multiple choice, or that's our answer. Here's a way to check. And it's kind of important to do this. So 3 comes down, right? 3 divided by 3 is 1. So when we take its derivative, we're going to get 5x squared. Oh, that's cool. That's what we had. Take the derivative of negative x, 8x. Well, take the derivative of something with just an x, x to the 1. The 1 comes down, you get your negative 8. Subtract 1, you get x to the 0. So we got our negative 8. Oh, cool. That's what we got. Take the derivative of natural log of x. So we get 3 times 1 over x, or 3 over x. And yeah, that's what we had here. Take this derivative, negative 1 comes down, so we get a negative 2. Subtract 1 from the exponent, we get x to the minus 2. Yep, that's what we had. Derivative of c is 0. Okay, so I took the derivative of what I got, and I matched that. So this will help you find if you made any errors somewhere. Okay, you didn't get exact, oh, I need to change the sign or something. But always do the check. It'll get you there. Okay, and now, sort of the final of the new stuff, at least. Give us some room here. So this is when one of the boundaries is a variable. And again, this is really going to set you up for Calc 2. You're going to be doing some of this when you do multivariable. You'll like do double integrals, triple integrals, and one of it is a variable. What we need to evaluate this is we need to do it so that the variable is on top. So we can do that simply by changing the boundaries going from 3 to x to the third, and we put a negative because this will be the opposite, because basically we're going opposite direction. Okay. Tangent to the 11 t dt. So we want the antiderivative of tangent to the 11th power. And let's see, I haven't thought through this too much. So tan t is a derivative. Remember, this is a derivative of something. And we want to find, oh, wait. Okay, I get myself confused too much. We want the derivative of this. So basically, we take the derivative of this. This is, remember, this is the derivative of something. When we integrate it, we're looking for that original function. And so now, but we want the derivative of that function, and really this is the derivative of the function. So it's really just going to be tan 11. But what we're going to do is we're going to plug in this upper limit, right? That's the upper limit. If this was just x, we would have x here and we're done. But by chain rule, let me show you the thinking. We're kind of thinking, okay, in general, whatever's here, I'll just do a simple t dt. When I plug this in, I'm going to get u du, right? The derivative of u. So I have to use a chain rule. Now, if this is just u to the 1 power, the derivative of u is 1, right? But if it's not, it's x to the third. So what is the derivative of x to the third? Well, that's 3x squared. So without getting too funky on the symbols, whenever we have something other than just x to the 1 power in here, we, through chain rule, have to use the chain rule derivative. So then we've got 3x squared. That's the key part. And a lot of times we put this in the front, right? 3x squared. Even though when we think about it from chain rule, we do the first part and then this is the back part. But this is just going to be the function, whatever they give us, because this, as you know, says to integrate it, the derivative is this part. Remember, we always get back to where we started with. And then we just have to say, okay, when this limit at the top, the boundary, the intervals of integration, when it's anything other than just x to the first, use the chain rule on it. Even with x to the first, we're using the chain rule, but we multiply by 1, so we're okay. I hope that makes sense. Do a little bit of review on the homeworks, but that's our derivative. So now I'm just going to keep going with this mastery exam review, and then we'll be done. So let's give a little bit of space here. This is the chain rule, so just be able to do that. And it gets a little tricky. X to the 5th times e to the 2x. So take the derivative of the first part, 5x to the 4th, times the second part unchanged. Okay, we'll do that, e2 to the x. Plus, take the first part unchanged, x to the 5, times the derivative of the second part. Well, the derivative of the second part is just e to the 2x. But remember the chain rule, we now need to take the derivative of the exponent. Derivative of 2x is 2. Okay, so that is an answer. Just be prepared. For multiple choice purposes, they may say, okay, let's factor this out. Let's do some algebra on it. So notice we can take out an x to the 4th. And we can take an e to the 2x out because they both have that. could factor those out, and then what's left, well, in the first one, all that's left is 5 because we took this x to the fourth, put it in the front, we took this in the front. So there's a 5. Second term, there is a 2x left. Both of these are correct answers. The thing is again, on a multiple choice test, you have to be able to identify which one is being used. They may use this one, or they may use this one. They're both correct, but be able to recognize them. Okay. And sometimes they do. They want to make sure you have understanding, and if they put this in, you might just be saying, oh, that's a product, or yeah, it's a product rule, so it's going to have a plus, and okay, you see that. Sometimes they think that might make it too easy by doing this extra step of factoring back the answer, that you have a deeper understanding. That might be how they look at it. Okay. And in this last one, this is not logarithmic derivatives because it's the derivative of a logarithm. So we don't have to take the log of both sides. So this one is just find y prime. Well, let me step back. Before we do that, we're just going to do algebra. We're going to take the log rules and rewrite this as a sum or difference of log rules. Now this, everything's being multiplied, so this will all be added together. So it's going to be 3 logarithms, this one, and this one. So I'll do it step by step. So natural log of x to the 11th plus natural log of x plus 12 to the 13th plus natural log of x to the 8th plus 9 raised to the 10th power. And the other logarithm rule we use is that the exponents can become multiplication in front. So we'll do that, and that makes taking its derivative just that much easier. You don't have to worry about chain rules so much, a little bit, because we still got stuff inside here, but it makes it simpler. Okay, so those are all going to come down in front. So really what I'm doing is 11 natural log of x plus 13 natural log of x plus 12. It's going to be pretty simple. Plus 10 natural log of x to the 8th plus 9. Now this one's going to be a little trickier. We need to use the chain rule on this one. The other one's, again, we always sort of use the chain rule, but let me just do this. But we don't think of it. So derivative here is 11 is just a constant. Derivative of natural log of x, I should do it this way, is 1 over x. So this just is 11 over x. Now using the chain rule, derivative of x is 1 times 1. Okay, so that's why we sort of use the chain rule, but we don't really think about it. This one, same thing. 13 is a constant. Everything here goes in the denominator, x plus 12. If we take the derivative of the input part, x plus 12, we just get 1, right? Derivative of x is 1, derivative of 12 is 0. So again, we don't do anything with that. We don't think about the chain rule, but it's sort of implied there's a times 1. Okay, this last one, we're going to get 10. Take the derivative of a natural log. Whatever the input is goes into the denominator. But this is the one that's going to be, that probably will throw you off if any part throws you off. We have to take the chain rule is then we take the derivative of the inside part. That's going to be 8x to the 7, right? Derivative of 9 is 0. So where does that go though? Sometimes you say, oh, should that go in the bottom? No, it's just kind of multiplied here. So it's actually in the top. So this is going to be times 8x to the 7th. Subtract 1 from the exponent. So this is chain rule part. So you'll probably see the answer as 80 x to the 7th. I'm not going to rewrite all of this for just that little cleanup, but that's what you would look for. Okay, so be able to take a derivative of a logarithm. Now, if one of these was in the denominator, basically that what's the nice part about we would have done this instead of having a plus, we would have had a minus for the part in the denominator, and it still makes taking the derivative pretty straightforward. Much more straightforward than trying to do this with a, um, I mean, you could put all of this underneath and then, but then you'd have when you do the chain rule part, man, that's going to be a mess because you've got a product inside here and the chain rule would be ugly. And then trying to simplify it down. So just, yeah, don't make things harder than they need to be. That's how I live my life. I highly recommend it. Uh, there we go. So that's the review, the brief review for the final exam. It's been great working with y'all this semester. I thank you for all your input, your understanding, your patience, um, and wish you the best of success on the final and beyond. Thank you very much.